Imagine you must program a temperature-dependent function like heater, sprinkler, fridge in an electronic monitoring device. The function must trigger upon temperature in Celsius degrees, but your thermometer measures in Fahrenheit. So, it is converted into Celsius using temperature conversion device control. Finally, it is showed up. Here, one process is substituted in another process to get final result. And this is called composition of function. Let us see how it happens. Now the question is, what is a composition of function? If f is a function from a to b and g is a function from b to c, then the composite function g of f, composition of f from a to c is defined as g of f of x is equal to g of f of x for every x element of a. Now let us see briefly through an example diagram. Here the function f, function g at g of f is shown. Alright. Now we shall see this through an example for better understanding. Let us consider three sets A, B, C. So the set A represents a set of class 10 students appearing for the board exam, and the set B represents the roll number given to all students. B belongs to a natural number, and the C represents the fake number that is allotted to all roll numbers. C also belongs to a natural number. Now what is this fake number? In board exam, all students write their roll number on their answer sheet. To maintain confidentiality, board arranges a fake code to all the roll numbers. Then the two function f of x and g of x arises, where f of x is the roll number that is assigned to the students in set A, and g of x is the fake code number that is assigned instead of the roll number in set B. In this process, each student is assigned a roll number through the function f, and each number is assigned a code number through the function g. Thus, combination of these two functions, each student is eventually attached a code number. Alright, now let us focus on some problem. Let f is equal to 2, 3, 4, 5 maps to 3, 4, 5, 9, and g is set 3, 4, 5, 9 which is mapped into 7, 11, 15 to be a functions defined as f of 2 is equal to 3, f of 3 is equal to 4, f of 4 is equal to 5, and f of 5 is equal to 9, and g of 3 is equal to g of 4 is equal to 7, and g of 5 is equal to g of 9 is equal to 11. Find g of f. Let's see the solution. To find g of f, we should use a formula, that is g of f of x is equal to g of f of x for every x element of a. So, g of f of 2 is equal to g of f of 2. What is f of 2 here? We got it as 3. So, g of 3. And what is g of 3? It is g of 3 is equal to 7. Now, g of f of 3 is equal to g of f of 3. And what is f of 3? That is 4. Now, what will be g of 4? The value will be 7. Similarly, g of f of 4 is equal to g of 5 is equal to 11. And g of f of 5 is equal to g of 9 which is equal to 11. Let's see the next example. Show that if f is a function from a to b and g is a function from b to c are 1, 1, then g of f is a function from a to c is also 1, 1. Suppose g of f of x1 is equal to g of f of x2. Again, this can be written as g of f of x1 is equal to g of f of x2. Given g is a one-to-one function, so we can write f of x1 is equal to f of x2. given f is one-to-one function. So we can write again x1 is equal to x2. So it is proved that the function composition of one-to-one function is always one-to-one. Similarly, the function composition of two-on-two function is always onto. Are f and g both necessarily onto if g of f is onto? Consider a is equal to 1, 2, 3, 4, b is equal to 1, 2, 3, 4, c is equal to 1, 2, 3. According to the definition, f is a function from a to b and g is a function from b to c. So, what can be the function f? F is set 1, 2, 3, 4 mapping to 1, 2, 3, 4. Now, what will be the function g? G will be 1, 2, 3, 4 mapping to the set C, that is 1, 2, 3. So, g of f is a function from A to C. Now, it is defined as, g of f is defined as f of 1 is equal to 1, f of 2 is equal to 2, f of 3 is equal to 3 and f of 4 is equal to 4. So, we get g of 1 is equal to 1, g of 2 is equal to 2, g of 3 is equal to g of 4 is equal to 3. So, we can understand the set C contains only 3 elements. So, g of 3 is equal to g of 4 maps to the same element 3. Here, g of f is onto, but f is not onto. Alright, next we are going to discuss another aspect of composition of function, that is inverse function. Probably the very first question will be, what is an inverse function? It is simply a reverse process of the composition of function. While composing f and g, to get g of f, first f and then g is applied. While in the inverse process, first inverse of g, then the inverse of f is applied. A function f from x to y is defined to be invertible if there exists a function g from y to x such that g of f is equal to ix and f of g is equal to iy. Then the function g is called the inverse of f and is denoted by f inverse. If g is invertible, then f must be one-to-one and onto function. And if f is one-to-one and onto, then f must be invertible. Now, let us concentrate on some theorems on invertible function. Before that, let's do one problem. State the reason whether the function has inverse. Where g is defined from set 5, 6, 7, 8 to 1, 2, 3, 4, the g is equal to set ordered pair 5, 4, 6, 3, 7, 4 and 8, 2. Let's see the solution. Here, given the function g 5, 6, 7, 8 to 1, 2, 3, 4 is defined as ordered pair 5, 4, 6, 3, 7, 4 and 8, 2. So, it is seen that g is a many one function as g of 5 is equal to g of 7 is equal to 4. So, g is not 1, 1. Hence, the function does not have an inverse. Now, we will move on to the theorems. First theorem, if f is a function defined from x to y and g is a function defined from y to z and h is a function defined from z to s are functions, then h of g of f is equal to h of g of f. Let's see the proof. According to the formula, h of g of f can be written as h of g of f of x is equal to, removing this o, so we get it as h of g of f of x, which is equal to, again we can write it as h of g of f of x for all x in x. Going from outside. Now take the RHS, that is h of g of f of x can be written as h of g of f of x, which can again be written as h of g of f of x for all x in x. So, comparing these two, we can understand h of g of f will be equal to h of g of f. Hence proved. Now, next theorem, theorem number 2. Let f is a function defined from the set x to y and g is a function defined from the set y to z be two invertible function, then g of f is also invertible with g of f inverse is equal to f inverse of g inverse. Let's see the proof. To show that g of f is invertible with g of f inverse is equal to f inverse of g inverse, it is enough to show that f inverse of g inverse of g of f is equal to ix. G of f inverse of g inverse is equal to iz. Now use the theorem h of g of f is equal to h of g of f. Our first theorem, using that we can solve f inverse of g of f will be equal to f inverse of g inverse of g of f. Applying the first theorem here. Now, this can again be written as f inverse of g inverse of g of f. By definition of g inverse, it is further reduced to f inverse of iy of f. What is this? This is actually ix. Similarly, it can be shown as g of f inverse of g inverse is equal to iz. Learning these aspects led me to a question. Is parabola a one-one function? And is it possible to find inverse for a parabolic function? So what we have learned is here all about the composition of function. Now let's have a quick recap.
Manorama Horizon. Learning made simple.